So, hello everybody. Today we have Iratxe Perales giving us her presentation. She's a CEO in the company Microphi Systems, and today's webinar title is Affordable, Simple and Fast Detection and Quantification of Spores in Honeybee Samples using Automated AI-based Digital Microscopy. So I will give our word to our respected presenter, Iratxe. I hope I pronounce your name correctly.
Yeah, it's difficult. Thank you for the presentation and good morning, everybody. I'll share my screen. Okay. Can you see it?
Yes.
Yes. Okay. I'll try to make it useful and easy to follow. Just a very brief presentation about our company and who we are. We are Microphi Systems and we do affordable automated devices for the agri-food industry. When we started our company, our mission was to provide with plug-and-play affordable devices for the industries that cannot afford like big and complex scanning microscopes, specifically designed for the pharma and medtech industries. So what we did is to robotize a simple microscope and to create an artificial intelligence module. So everything is fully autonomous, the scanning of the sample and also the image processing. And we try to make it very affordable for all entities and very easy to use, like without any type of previous experience, everybody could use it. We are 8 people in the company. We are based in Barcelona, in Spain, and we have engineers, biologists, and also mechanical designers. And we do different applications like spore counting, texture assessment, object detection and classification. So the sample is scanned automatically, and then the image is processed in the cloud. The first product that we started to develop was Honey AI, which is an automated microscope that is specifically designed for the honey industry. And we started with the pollen analysis. Then we developed other applications. So at the end, the microscope can do the pollen analysis, can do honeydew elements, crystallization rate assessment, color measurement, yeast content, conductivity with external proof. So at the end, what we wanted to develop is something useful for the honey industry. Here you can see how the pollen grains are being focused and how the microscope scans the sample. And this is very brief images about the pollen grains. So when we started to sell the device to different cooperatives and associations and universities working in the honey sector, we talked to them and we asked for other different applications that we could develop for them, also with the same microscope. And talking with the Spanish ministry, with the Veterinarian Center of Algete, which is the national reference lab in Madrid, they explain us about the Nosema counting that they do manually. So they do everything like traditional counting with bright field microscopy. And we asked them if it could make sense to automate this functionality in the same device. They liked the idea and they told us to help us to develop the system. And that's how Nosema AI started. The nosemosis is a disease that in the past it really impacted in the beehives. It was mainly applied by Nosema apis, and the first disease that was nosemosis type A was, let's say, quite easy to diagnose on the field because it has very clear symptoms like diarrhea and deformed wings. So the veterinarians and the beekeepers, for them was quite easy to diagnose on the field. But then Marchamalo Center in, I think it was 2003, started to publish some papers with the nosemosis type C, which was with nosemosis by Nosema serrani. And in this case, the diagnosis was not so clear because the clinical symptoms were different. And Nosema apis, it was very seasonal, but then with Nosema serrani, what it was seen is that it was along all year, and the symptoms were different. There has been a lot of publications based in nosemosis, and it is true that it's not so serious as Varroa, because the mortality related with nosemosis is not directly linked. But what it has been clearly seen is that nosemosis has a serious impact in the beehive because the bees started to be more weak. So when it's combined with another external effects, it has been clearly correlated that the mortality is higher. So alone, the nosemosis is not a problem by itself, but when the beehives are infected with different nosemosis, then when other external factors like Varroa or other different um, disease or external weather factors complement the nosemosis, then the beehives can collapse very easy. And the problem is in Europe, the treatment with fulmagilina is forbidden because it has been clearly demonstrated that there are residues in honey. So today there is no clear solution and treatment for the beehives because the ESA has forbidden the use of Fumagelina. So now there are different treatments based in probiotics and postbiotics, and also different supplements, because it has been clearly demonstrated that good supplements applied to beehives help them to overcome the problems of nosemosis. Because if you supplement correctly to the beehives, then the weaknesses of the nosemosis are reduced. So now what we are proposing is better and more frequent monitoring of the beehives to check if the strategies of supplements are correctly done, and if really the infestation in the beehive for Nosema, if it's kept under control, then the effects are, let's say, corrected over the year. The problem is that monitoring the infestation load in the beehives, it's difficult because you need an expert. You need to work with molecular techniques, with PCR, which is expensive, and you need to have the equipment. Or if you want to do it with manual techniques, you still need a microscope, and you need to be an expert. And you need like labor intensive work because you have to do it by hand. And it is true that there are centers that you can send samples and then they do the diagnosis for you, but in some of them you have to pay, and another, if they are free, you still have waiting times. So what we are proposing is an automated tool that you can use with our Honey AI microscope, and everything is automated. It is very fast, it is very accurate and sensitive, and there are no waiting times because you can do it at your premises in 5 minutes. So here I present a little bit how the project started. The provisioning of samples, both for Apis and Serrane, was done by the Spanish ministry, the Center of Algete. They provided us with infested samples for both, and they sent us the samples, and they help us to create data sets for us. And then we started to develop the data sets, the AI algorithms, also to define the scanning protocol for our systems. It was done here at Microfy, and we had external help from a digital innovation hub from Valencia, the Informatics Institute of Valencia, that help us to better measure the dimensions of the microorganisms. And then the last stage has been done by Neovator and the University of Extremadura. They have done the testing and validation with real samples. So the pipeline that we implement is first, we implement the calibration and the image analysis of the samples in the microscope. So you, as a user, you first put the sample, then the scanning microscope finds where the calibration and the best focal plane is, and then we start scanning the images. Then we have a first model for detection of spores in the full image, and when we have detected the microorganisms, then we look for the first focus and detect where the particles are. And then we also have a classification based on the shape, the color, and the dimensions. The dimensions of the particle help us to classify and dismiss yeast Nosema spores. And then when we have correctly classified the spores of Nosema, then we also do an estimation of the species. So we are able to tell the user if the spore is Nosema apis or Nosema ceranae. It is true that in most countries we can hardly find Nosema apis. Nosema ceranae has already invaded most of the beehives, but in some beehives we still can find a small concentration of apis. So based on the width and the length of the particle, we can tell the user if the concentration is from apis, from ceranae, or both, if it's mixed. So in the dataset, we already did it. We have like 3 minutes for sedimentation and 7 minutes for scanning. So at the end, the Nosema analysis requires around 6 minutes. Then the user has to use a specific volumetric chambers that has more than 10 times largest volume scan compared to Neubauer chamber. This is good because it makes the system more sensitive, and we scan 20 locations. So considering a sample that it has a low load of spores with our system, because we can scan 10 times more volume than the Neubauer chamber, it is much more sensitive. And then we don't use consumables like the PCR. So what we did is to scan, to analyze different protocols for Nosema manual counting with microscopy in different countries and different regions and different organisms. We review the state of the art to identify how the sample was collected and prepared. Also, we reviewed interlaboratory studies for Nosema with traditional method, and we review manual procedures and criteria. We also work with different objectives at 40 and 60, and we checked phase contrast versus bright field. So at the end, what we implemented is a recommended protocol with 60 adult workers, also working with the 60 objective instead of 40, because it helps the system to discriminate between yeast and Nosema spore, and also the BD chamber, which is the specific volumetric chamber that also you can use like 50 times, like Neubauer chamber. So there's no problem with using it many times. And also we recommend using a stomacher bag with 200 microns spore size, because when you filter the sample, it makes the sample, let's say, a little bit more clean. This is how the PDF of results look like. So when the user finalizes the analysis, there is a PDF of result in which you can see the number of spores per bee, also the degree of infestation. Also, you can see images, so you can directly see the fields that microscope has covered. And here in the table, you can see estimation of different species based on width and based on length. There is one specific percentage that is where the sizes they overlap. So it's like when we cannot be sure if it is Apis or Serane because the dimensions overlaps between species. But then in width and length, in the sizes, when we are sure about if it's Apis or Serane, there is a histogram of sizes. Here is a video about, it's only 10 minutes, but very brief, like how it works. Here you can see how the sample is prepared. This is the EBD chamber. Once that the V sample has been prepared and filtered with the stomacher bag, then you put the sample in this specific channel. Then this specific slide, we provide the user with this system. The sample is prepared very easily, and then you put it in the automated holder. Then the objective of 60 has to be chosen. The microscope is connected with the APP, and once that is correctly placed in the holder, then the APP can start, and the user can include the information about the type of test, observations, if you want to include whatever about sample origin, and then the user can start the test. As said, everything is autonomous. So once that sedimentation time has ended, which is 3 minutes, to let the spores place in the sedimentation plane, it starts scanning and looking for the spores. Here you can log in the dashboard, and in the dashboard then the user has all the historics of the analysis done, and then you can download the PDF and you have all the information as I already showed, with the plot of the dimensions and also the pictures. So you can also access the real pictures that we have. This is the validation that we did. Neovator is a spin out from the University of Extremadura here in Spain. I think there are 5 researchers working then. I think it's private company, but from researchers from the University of Extremadura. They are biologists, experts in honey, and veterinarians. And what they did is a validation for us. We sent them the microscope, and they use 50 real samples. And what they did is to use our microscope 2 times to check the repeatability. Also, they compared our values with the qPCR duplex for Serane and Apis, and also they also did traditional bright field microscopy with normal counting. The conclusion was 95% F1 score on the validation set, high correlation between manual and AI-based counting, with 0.94 correlation and specificity above 80%. They reported as good usability. And the only problem that they confirmed was that the Nosema spores that were placed in transversal plane, because they look like circle, rounded, the AI model was not able to always identify correctly. They reported that even for humans, sometimes they did not count these rounded spores because of the shape circular. So even for them was very difficult to identify and count. They told us that the system is more sensitive than the technique with PCR and traditional microscopy for low loads, below 1 concentration, 1 above 10 at 4. So for loads very low, that no-bower chamber was not an able technique, or for high load that they had to dilute because otherwise a human could not count it with high loads, the microscope was extremely useful for them. Here you can see like real pictures. This sample is quite clean. It's an easy sample. Here you can see that the squares in green, it's positive detection of Nosema, and the squares in red were negative, like where the AI said that there is something, but it is not Nosema. And here you can see another sample that was not so clean, that it has a lot of dirt, and still with a lot of dirt and particles, you can see that Nosema did very well. Green for Nosema and red for other particles, microorganisms that could seem similar to Nosema, but AI said that it is not. So here you can see in the picture that even for a human could be like very tough and exhausting to count the Nosema. So in this case, for the machine is very fast, and for the human could be very tough. Here I can show you the estimation of a species. This is what we got as results of the 50 analysis, so 50 samples. This is the plot that we obtained with all the sizes. The samples were all positive to Serane, and not positive or not definitive for Nosema apis. So here you can see that based in length and width, here you can see the line in which based on dimensions, it should be Serane or apis. So there is percentage in which we cannot be sure in non-definitive, non-positive values, but all the others we could clearly see that the spores were Serani. The references that we used for the dimensions were from one thesis done in Marchamalo Center. I can share with you the specific thesis that we used if you are interested in. One problem that we had is that for us it was not possible to use pure API samples, and that's why we could not clearly analyze a sample with only IPs. If any of you know how we can test with pure API samples, then it would be extremely useful. And now we are working with the Pollinator Hub to be able to work with them. So everybody that use our system, if they consent to transfer not their data but their results, the system could be integrated with the hub. So everybody that wants to access Pollinator Hub and check Nosema incidence in Europe could have free access to our data and to check real results from different regions. We have a meeting next week with them, and we will integrate all the information for those users that accept to communicate the results, not the data of their, let's say, of their identity, but only the results, like region and results. And yeah, now we are offering free trial periods with early adopters, between 2 and 3 weeks free trials, to provide insights and feelings as end user. So if any of you could be interested, now the Spanish ministry would be using it during February, 3 weeks, and also other entities in Europe. And yeah, the project has been partially funded from Spanish government and European Commission, and also Catalan government. And thank you very much for your time. And if you have any questions or any comment that you want to share, I'll be glad to solve your doubts.
Thanks a lot for this such nice presentation, Iratxe. We have one question from Gordon. He asks how large are the spores?
The spores are I think it's from 3.5 microns up to 7. Let me show you again. But maybe it's too small. Here are the sizes. Here it's Serrane length is from 3.6 to 5.5, and the width from 2.3 to 3. And Apis, which is a little bit larger, length is from 5 to 7, and width from 3 to 4. So here you can see that in width, there is no overlapping, theoretically, but in length, there is a little bit overlapping. The problem is that when the spores are placed in transversal, then you cannot be sure. You only can be sure about length and width when they are like perfectly placed in horizontal focal plane.
Mhm. Okay, thanks. I have one question also. How much time did the AI take to learn these things to differentiate the spores in length? And how long did this project last? I hope I'm.
When we were training the model, you mean?
Yes.
Okay, it has been like few months iteration.
Mhm.
The main problem was to create the data sets, because we first had to ask for infested samples to the Spanish ministry, and public institutions, when it's government, everything has a lot of bureaucracy. So for us, it was like 3 or 4 months until we got the infested samples. Then we had to create the data sets, that it was 3 months also. And then when we created the models, we had to iterate a lot of times. And also we had to create a specific segmentation model to identify very accurate the dimensions of the sample, and then to measure. So to launch the training was 1 week, but then to iterate and implement better models, maybe what was 3 or 4 months more.
Mhm. Nice. Thanks. We have one more question. Two questions more. Firstly, from Diego. Nosema smells something special in the beehive. I'm not sure if this question is really clear.
If it smells,
Yes, I suppose.
I don't know. I know that for the diagnosis in the beehives for Nosema apis, it was mainly done by the deformed wings and the diarrhea in the panel, in the front panel. But now for Nosema serrane, it's very difficult. There is not clear symptoms, and usually it can be like problems that it could be also other disease, like decrease in production of honey, like just bees, like abandoned symptoms, and also the form bees, like smaller bees.
Mhm.
But I don't know about the smell. I never
Oh,
learned about that. I can ask.
we have a question from Eva now. Do you recommend diluting dirty, dense samples?
In this case, when you have the worker smashed and filter with the bag, in case that the load is very high, for the microscope is not a problem, because it can count hundreds of spores. If you want to do it like naked eye as manual inspection, then you have to dilute for sure.
Mhm. One more thing from Gordon Hunter, our professor from UK. Your system seems to have quite a lot similarities with one of our Varroa counting, which I recall we discussed during the Larissa conference last May. So yeah, it's probably
It's the difference, I would say, it's that is coupled with the automated hardware. So at the end, what we are doing for detection and classification of microorganisms is like state of the art. So there is a lot of literature and papers published already for applications like this one. Um, I would say that the novelty is that is coupled with a scanning microscope, so everything is autonomous, and also that we are trying to differentiate species that I think that has never been done before, trying to tell the user if there is apis and serrane and the load of each one, because until now only PCR was able to do that, but with naked eye it's impossible.
nice. Thanks. Do we have any more questions, maybe? I suppose if that's it.
Okay.
Thanks a lot, Iratxe, for giving your presentation and for responding to my email so quickly.
Thank you very much to everybody. And if any one of you want to try, just let us know.
Okay. We will have the next webinar is scheduled also for the last Monday of the February. So I will contact you guys so you know when we have the exact time for that webinar. So
Okay.
thanks a lot
Thank
for
you.
joining today, and hopefully we will see each other soon again.
Okay. Bye bye.
Bye.
Bye bye.